Inverse trig derivatives. Well, the first thing you need to know about inverse trig functions is they have what we call restricted domains. We saw this in pre-calc, but again, just in case it's rusty or maybe you've never seen it before, I'll talk about it again because it's important. We know what the graph of sine and cosine both look like. They're nice, smooth curves oscillating between 1 and -1. Now, if we were to do the graph of the arcsine, it would look like this. So again, the top graph is the sine function. The bottom graph is the arcsine function. Oh, wait. I just called the bottom graph a function. But it violates the vertical line test a lot. And I've got to do something about that. So here's what mathematicians did, because we need to use arcsine as a function in the calculator. So what they did is they chopped it right here and right here and just pretended that the rest of this never happened. Nothing to see here, folks. And they just used that part of the graph, which actually does obey the vertical line test. And that ends up being the part of the graph that's between positive pi over 2 and negative pi over 2. Same thing with tangent. The graph of tangent, as you guys know, is a bunch of repeating, it almost looks like S-curves, and they have asymptotes in between them. If you were to flip this around and make it an inverse function, it would look like this. Which again is no good. That's a bad violation of the vertical line test. So what the math minds did was they said, okay, look, let's just take this middle one, the one that's, closest to the origin, that goes through the origin, and the asymptotes are x equals pi over 2 and negative pi over 2. Let's just look at it only and forget the rest. That way, when we dump it sideways, these won't exist. We'll just have the middle one. And that's why, again, arctan is only defined between negative pi over 2 and positive pi over 2, or negative 90 and positive 90 if you like degrees. And again, cosine, the cosine graph is just the sine graph shifted 90 degrees, so it's going to do the same thing. It's going to be defined between 0 and 180. And again, the reason that this all has to come about, this how come, you have to obey the vertical line test to be a function. So my expectation is that you will remember these and keep these in mind. It helps to know that sine and tangent are both odd functions, and so therefore they sort of behave alike. The cosine function is even, and so it's sort of the different one, if you will. I was almost going to say the odd man out, but I don't want to say odd because it's even. All right, let's look at some examples. Okay, easy enough. It says evaluate without using a calculator. If you use a calculator, I'm going to know because you're going to get a 10-digit decimal and everybody else is going to get an exact answer that's either a fraction or a square root in it, and you're going to be exposed. So you can check it with a calculator, but don't expect a calculator on a test or quiz. I would put this on the non-calculator section. All right, it's the cosine of the inverse or arctangent of negative 3/8. Oh boy. Okay, the way I teach this is I make up a variable. I think I'll just start in the beginning of the alphabet. I'll start with A. And I call this part A. In fact, I write a note to myself. A is the arctangent of negative 3/8. All right, from what we learned in pre-calc, and even in Algebra 2, is if you want to get rid of this little irritating -1 inverse symbol, and who wouldn't want to get rid of it? You can, just by switching the x's and y's around. Except that we don't have x's and y's, we have a negative 3/8 and an A. But hey, same deal. Switch spots and it becomes a regular tangent. So the A goes to the right, the negative 3/8 goes to the left. All right, fabulous. At this point, I want to go ahead and do two things. I want to know where I'm at as far as quadrants. So I'm going to make a quick graph of the 4 quadrants. Remember that in quadrant 1, everything's positive, all 3 functions. Then just sine is positive in quadrant 2. Quadrant 3, it's tangent. Quadrant 4, it's cosine. You should know this from the past. If you go counterclockwise, A, S, T, C, all students take calculus, which is a total lie. So I say all students take classes. All right, I need the tangent to be negative. So what that tells me is obviously I can't be in quadrant 1. And I can't be in quadrant 3. I'm either in quadrant 2 or quadrant 4. But wait, I was using an arctan. And from the previous slide, I know that arctan has to stay between 90 and negative 90, between pi over 2 and negative pi over 2. And if that's the case, here's 90 degrees up here. Here's negative 90. If I have to stay over here, I can't be in these quadrants. I can't be in quadrants 2 and 3. So therefore, that tells me that in this particular problem, number 1, I have to be in quadrant 4. I've eliminated this. I have to be in quadrant 4. Let's jump back over to here. I'm taking the cosine of angle A, and I know that angle A is a quadrant 4 angle. Well, my answer is going to be positive then. Positive something. I don't know what the something is yet, but if I'm taking the cosine of A and I'm down here in quadrant 4, it's not going to be negative. So that's good news. All right, let's make a triangle out of this using SOHCAHTOA and some geometry. Just make a random right triangle. It doesn't have to be an artistic work. I'll pick one of the 2 angles that's not the right angle. I'll pick one of the acute angles, and I'll call it A. I don't know. I'll pick this one. Okay, that's angle A. According to what I circled up here, tangent of A is 3/8. So tangent from SOHCAHTOA, that's TOA, tangent is opposite over adjacent, TOA. So 3 and 8. Now notice I said the tangent of A was 3/8. It really was negative 3/8, but to be quite honest, I don't care about the negative sign anymore. I already know that my answer is going to be positive something, so I can just ignore all the negative signs for the rest of the problem, which I think is fantastic. All right, let's finish out my right triangle. I can use Pythagorean theorem. 3 squared plus 8 squared. Oh boy, let's see, that's going to be 9 plus 64. This hypotenuse will be the square root of 73. Okay, what am I trying to do? What am I trying to do? What the heck? Let me cover this up a little bit. Oh, I'm trying to find the cosine of A. And I happen to have a triangle with an A in it. This is going to be easy. Cosine is ka from SOHCAHTOA. That's adjacent over hypotenuse. So the answer would be 8 over the square root of 73. I'm going to make my Algebra 2 teacher proud of me and rationalize it like I was taught last year, although you don't really have to in calc. And the answer to number 1 is 8 rad 73 over 73. And unless you're some sort of mathematical savant, you're not going to type that original thing into the calculator, get a 10-digit decimal and go, oh, wait a second, I see it. Yes, 8 rad 73 over 73. Yeah, nobody normal does that. Okay, and I realize that. So if I take your calculator away and you're giving me, 10-digit decimal answers, I know you've got a calculator somewhere and you're looking at it. Yeah, that's a dead giveaway. So you should be able to do this without using technology. All right, number 2. Same thing, evaluate without using a calculator. I used the letter A last time. Let's go for a B. And I'm going to make a note to myself that B is the inverse cosecant of negative 9/7. Switching positions allows me to say that the cosecant of B is negative 9/7. That got rid of the inverse. And if the cosecant of an angle is negative 9/7, then the sine would be negative 7/9. That's what I'd prefer. Let's get a little triangle made here. And this time I'll pick the other angle, just to be equitable. Angle B. Okay, sine is opposite over hypotenuse. All right, so that looks pretty good. Let's grab that other side over here. This is the short side, so I have to subtract 9 squared. 81 minus 49, that's going to be 32. So that's the square root of 32. And by the way, the square root of 32 happens to be 4 rad 2. I think I'm going to simplify that. That'll make my life easier later on. Okay, one more thing that I have to consider, and that's where am I? Which quadrant am I in? Well, right here where I'm putting these stars, it says that sine of B is negative. If the sine is negative, clearly you can't be in quadrant 1 because everything's positive there. Sine would also be positive in quadrant 2, so I can't be in quadrant 2 either. I must be in 3 and 4. But again, remember I had an inverse cosecant in this problem. And by the way, the reciprocal functions behave the same way as the regulars. So since cosecant is the reciprocal of sine, the inverse cosecant will also only be defined between 90 and negative 90. So you also can only stay in quadrants 1 and 4. You can't be in 3. In fact, the inverse functions, you can never be in quadrant 3. Quadrant 3 gets honestly completely discriminated against. It's totally not fair. But if you look back at the first slide, we already saw that inverse tan has to stay in quadrants 1 and 4. The same thing with arcsine. It has to stay between 90 and negative 90, so it has to stay in quadrant 1 and 4 as well. Arc cosine, being between 0 and 180, has to stay between quadrant 1 and quadrant 2. This poor quadrant 3 down here just gets no love. It's seriously just kind of off by itself. So the calculator will never put you in quadrant 3. Interestingly enough, if you're in degree mode and you type in something like inverse sine of, you type in some decimal, I guarantee you, you will never get an answer between 180 and 270. The calculator is trained not to go here. No. Interesting. And the reason why is because the calculator can't throw you 2 different correct answers on the same screen. It would be violating the vertical line test if it was to do so. Plus, the screen's only so big. Okay, back to what I was just doing. Okay, once again, I'm in quadrant 4. By the way, if you have a negative in your problem, you have a 2 out of 3 chance of being in quadrant 4. Because remember, you're never allowed in quadrant 3, ever. If you're negative, you can't be in quadrant 1. And so between sine, cosine, and tangent, 2 of them land in quadrant 4. The cosine will land you in quadrant 2. So if it feels like we're in quadrant 4 a lot, yeah, mathematically the odds are we will be 2/3 of the time if you're dealing with negatives. All right, so I'm in quadrant 4. Angle B is a quadrant 4 angle, even though I've got it in a triangle. If angle B is a quadrant 4 angle and I'm taking the cotangent of B, my answer is going to be negative. My final answer is negative something. Because cotangent and therefore tangent is negative in quadrant 4. Now that I know that my final answer is negative, I don't need to pay attention to like this negative or any other negatives in the problem because I know my final answer is negative. I got it covered already. I don't have to deal with it. What am I trying to do? Oh, yeah, I'm trying to figure out what the cotangent of B is. I've got a triangle right here. Let's use it. The tangent of B would be opposite over adjacent. So the cotangent of B would be adjacent over opposite. So the answer is going to be 4 rad 2 over 7. Negative, of course. See, just like everybody else, I get so into the numbers and so excited about the 4 rad 2 over 7 that usually I forget to put the negative sign on my answer. And so therefore, since I know this about myself, I deal with it first. I get it on there so I can't possibly forget. And now I know I'm right. Okay, no calculator, evaluate this. Again, just like before, we're going to keep to our methods. We're going to call that C. I'll write a note to self. C is the inverse secant of negative 10/9. Well, let's get rid of the inverse. So the secant of C would be negative 10/9. Again, we're just switching places between the x's and the y's, or in this case, the C and the negative 10/9. That gets rid of the inverse symbol. If the secant of C is negative 10/9, let's use some reciprocal golden sheet. That means that the cosine of C will be negative 9/10. All right, I need to do two things. I need to figure out what quadrant I'm in, and I need to make a right triangle and use some SOHCAHTOA. It doesn't really matter what order I do this in. Let's go for the quadrant this time. I see that cosine is negative. So I can't be in quadrant 1. I can't be in quadrant 4. I also see that I'm using an inverse secant, which is the reciprocal of inverse cosine. Normally, arc cos has to stay between 0 and 180, so I must be in quadrant 2. That's where I'm going to be. Remember, you're never in quadrant 3. You can put an X through that before you even start. Okay, so this is a quadrant 2 angle. I'm taking the tangent of something I know is in quadrant 2. Up here in quadrant 2, tangent is negative, so my final answer is going to be negative something, and I've already dealt with the negative sign. That's my Achilles heel. All right, let's pick an angle in the triangle. I'll pick this one again this time. We'll call it angle C. And cosine, as we know, is adjacent over hypotenuse. Notice I don't have to use or deal with this negative sign anymore because I already know that my final answer is negative. I got that taken care of. Using the Pythagorean theorem to find the short side, it's going to be 100 minus 81. That's the square root of 19. Little guy there. All right, what am I trying to do? Well, I've rewritten this. I'm simply trying to figure out, hey, what's the tangent of C? And so I can use my triangle here, and tangent is simply opposite over adjacent. Sure, you can plug the original into the calculator. Let's be really honest, if you even know how to plug that in the right way. You could get this answer, but the thing is you probably wouldn't recognize it as negative rad 19 over 9 just by looking at the decimal. I certainly wouldn't recognize it. But you could check all the answers with a calculator, which is really kind of cool. So, again, on a test or quiz, this would be a non-calculator section. All right, let's go with D this time. Getting rid of the inverse symbol gives me cosine of D is 5/6. I cut you guys a break this time, and I made the 5/6 a positive number already. That immediately tells me that I'm in quadrant 1. This is where we're going to be. And I know that because if the cosine's positive, I can't be in 2 and 3. And the inverse cosine, which is what we started the problem with, has to stay between, as we know, 0 and 180, so I can't be at 4. So yeah, if you see positive numbers, you know you're going to be in quadrant 1 on any of these inverses. So that's cool. And since I'm going to be taking the cosine of D, I know that my answer is also going to be positive. So the answer is positive something. All right, I make a triangle. I'm kind of laughing at myself. I don't know if you realize this yet or not. Everything I'm doing right now is a complete waste of time. All right, angle D. Cosine of D is adjacent over hypotenuse. All right, let's get this other side. I don't know why I'm doing this, but 36 minus 25 would be 11, so rad 11. And then I'm like, hey, what am I doing? Oh, I'm trying to find the cosine of D. Well, cosine is adjacent over hypotenuse, and the answer is 5/6. At this point, you're wondering why all your friends are laughing at you. Probably because you already had the answer right here. You didn't need to make the triangle. You didn't need to find the rad 11. Honestly, because it's positive, you probably didn't even need to figure out what quadrant you were in. In fact, you really didn't have to do anything. And the reason why is cosine and inverse cosine are, well, they're inverses of each other. So it's not surprising that the answer is just 5/6. So sometimes the textbook will have a little fun with you, and so will I. You know, we'll put a super easy problem on there and see if people do all this unnecessary work. Now, if this is negative 5/6, however, then you have a 50-50 chance of being correct. Then you probably should, try to figure out what quadrant you're in at least, because it could be 5/6, it could be negative 5/6. But if it's the same trig function both times and one's inverse, then don't make a triangle and stuff. Don't do the extra steps. Okay. All right, now it's about to get real. Oh dear. Okay, you have to memorize these. That's the bad news. There are 6 of them. You need to know them. I'm not being mean. College Board's going to make you know them. All your college professors, if you go into STEM fields, they're going to expect you to know these. The good news is you don't have to memorize all 6. You only have to memorize 3, the ones in red. Because if you look at the ones in blue, they're the exact same things. They just have a negative 1 in the numerator instead of a positive 1. And in fact, you don't really need to use the ones on the right. I never use them. If I see the word co in front, I just throw a negative on and I just memorize the 3 on the left. With helping to memorize, I remember that the derivative, and by the way, that D stands for derivative. Remember, sometimes you can say D or you can say dx, ddx, dy dx. It all means the same thing. So the derivative of arc sine of u is 1 over the square root of 1 minus u squared, and then times du. That du at the end is a chain rule. All those du's are chain rules. 2 out of the 3 have square roots. The one that's the nicest is the arctan. I always root for arctan problems. These do have some similarities. They all have 1s in the numerator. They all have 1s in the denominator. They all have u squareds. It's just a matter of, is it a plus? Is it a minus? Do you have square roots? The arcsecant's got that nasty absolute value of u in front. So you just have to kind of be on the lookout for them, and you just really have to memorize these 3. If you're willing to get the problems right, you'll have to do so by a little bit of memorization. If you choose not to memorize the inverse trig formulas for derivatives, you can reinvent the wheel every single time. You can prove all 6 formulas. I'm going to do so. Obviously, I'm not going to do all 6 of them. That would be incredibly boring. I'll just prove the arc sine one to you. I'll prove that the derivative of arc sine of x should be 1 over the square root of 1 minus x squared. Now, I'll do that right now. I'm not a big fan of the inverse symbol, so I'm going to go ahead and switch the x and y's, and that can get rid of it. So that'll leave me with x equals sine of y. So far, so good. I guess it goes without saying that if I want to prove something about a derivative, I might want to actually take a derivative. So I took derivatives of both sides. The x became a 1. The derivative of sine of y, of course, is cosine of y. Oh, that's the wrong letter. dy dx. There's the forgiveness parentheses, if you will. Implicit differentiation. It's a chain rule. And then finally, I'm going to divide both sides by cosine of y because, you want the dy dx by itself. So I'll do that. And I don't like the dy dx on the right-hand side, so I'm going to switch the order around to lead off with it. Okay, so far so good. I'm running out of room, so I want to scroll a bit. Now, you might assume that the next step I'm going to say, hey, the right-hand side is secant of y, 1 over cosine. And it is, but I'm not going to go in that direction. I'm going to do something totally off the grid. I used the golden sheet, the fact that sine squared plus cosine squared was 1, and I rewrote the cosine of y as the square root of 1 minus sine squared of y. Wow. All right. Sine squared of y is actually sine of y times sine of y, of course. Sine of y, that is familiar sounding. Sine of y. Sine of y. Oh my gosh, right here. Sine of y is x. Holy smokes. So I can replace the sine of y with an x, and there's the memorized formula. Now, of course, in the things that I had you guys memorize, I used the letter U instead of X. The book uses U as well. That's because a lot of these you're going to be seeing substitutions and you're going to have chain rules. So it doesn't really matter what variable you use as long as you're consistent. All right, right now people are probably getting a little worked up, a little nervous. This is much easier than what you would think. I think you'll feel better when you see me work through some problems. Number 5, 6, and 7, I think will build your confidence back up a bit if it's shaken. Okay, here's number 5. Find dy dx. So let's take a derivative. Of course, the 4 being a coefficient is just going to sit out front. I'll make it 4 over 1 since I know I'm going to have a fraction here. And this is the brand new stuff. It's the arcsine. So I know that the arcsine has the square root in it. Only arctan does not. I know there's a 1 on top. But because of chain rules and stuff, I'm going to call this u. Now, this is not a u sub. I'm not integrating, but I'm still going to call it u. And so the formula says it's 1 minus u squared inside that square root. And then the formula said times du at the end. And as I mentioned moments ago, du is the chain rule. Does this u have a derivative? Well, yeah, times 2. Okay, we'll do that then. And that'll give you the final answer of 8 over that lovely square root. I would advise you not to FOIL the 2x plus 5 in the final answer. Don't square that out. Don't combine it. Just leave it alone. Remember, the reason that we do derivatives is so we can plug numbers in. It's a much easier plug-in to leave it the way it looks now. And also, too, I realize that in Algebra 2, you wouldn't dare leave a square root in the denominator. But hey, you know what? You're not in Algebra 2 anymore. We leave square roots in the denominator all the time in calc. In fact, I've told many of my classes I feel like such a hypocrite because there were several years back at Brecksville where I taught Algebra 2 and calc at the same time, same year. And one class would leave, and I'd be like, don't you dare leave a square root in the denominator. And then the bell would ring, and the other class would come in, and I'm like, yeah, it's cool. You can leave it down there. I was like, wow, who am I? All right, so yeah, just leave it. All right, number 6. It's an arctan. So dy dx equals 1 over. Now, arctan is the one that does not have the square root. So it's 1 plus u squared. Again, this is the u right here. Sometimes I like to label it. Okay, so that's the memorized formula part. There is a chain rule times du. Does this have a derivative? Well, yeah, of course, it's an 8. And so your answer is just going to be 8 over 1 plus 64x squared. Now, it's up to you whether you guys actually want to square this or not. What you don't want to do is call the denominator this. That's wrong. This is fine. This is fine. This is not fine. Okay, so for that reason, I usually will just square it out. Again, you don't want to FOIL like number 5. You don't want to do all kinds of crazy extra work, but 8x times 8x is not that hard to figure out, so usually I'll do it. Here in number 7, we see past meets present. Yep, it's chapter 2 colliding with chapter 5. We've got ourselves a product rule with a u and a v. All right, here goes. Derivative equals u prime v. I'm going to slow myself down. U prime v. Let's copy it all down nice and slowly. Okay, u prime v plus u v prime. Well, since it's cosine, I'm going to put a -1. But after that, it's the same formula that sine would have been. So it's 1 minus this thing squared. I hesitate to call it u because I already have a u written on the page, but you know what it is. All right, so I've got that. And then times the chain rule of this, if this has a chain rule, which it does, so times 7. I'll just throw the 7 over here. And then that second part can be kind of cleaned up a little bit. It's going to be minus 21x squared in the numerator. And there's our not too attractive yet correct answer. All right.
All right, last example of this section, number 8. Find the derivative, dy dx. We start out with a product rule. Okay, so this will be the u, the x. The arctan of 3x will be the v. And then we've got some natural logs mixed in as well. So we've got inverse trig, we've got chain rules, product rules, we've got everything. Fantastic. All right, dy dx. U prime is 1, so u prime v will be 1 arctan of 3x. Plus u, which is the x, v prime, and this is our new formula. Arctan, so it's going to be 1 over 1 plus, and this 3x is the u, so u squared. 3x times 3x is going to be 9x squared. Times a chain rule of 3, because 3x does have its own derivative, and that's going to be 3. All right, and then the natural log portion of this will bring the negative 1/6 down. The derivative of natural log of anything is 1 over the stuff. Times a chain rule, does the parentheses have a derivative? Well, of course it does. Be 18x. I'll make that into a fraction, put a 1 underneath it. I'll make these other things into fractions as well. Why not? If you can't beat them, join them. All right, let's clean up this mess a little bit. Let's make this into a single fraction. Up top, we have x times 3. That'll be 3x. Down below, just 1 plus 9x squared. Let's do the same thing over here. Minus single fraction. Oh, we can cancel a little bit. We got the 6 and the 18. That'll be a 1 and a 3. And so that's going to be 3x over, my gosh, the same thing. Those two green things are opposites. They just add up to 0 and cancel each other straight out. And so the answer to the problem is simply right in front here. The derivative is arctan of 3x. And that does it for inverse trig derivatives. Hope you enjoyed it. See you later.